Before Hubble, space looked blurry. Astronomers on Earth stared through turbulent air, peering past the distortions of our own atmosphere. Stars twinkled, yes, but that shimmer was an obstacle, not a gift. Then in 1990, a school bus-sized telescope was launched beyond that atmosphere into low Earth orbit, where it could finally see the universe with unprecedented clarity. That telescope was the Hubble Space Telescope, and nothing in astronomy would be the same again. At first, it seemed like a disaster. Hubble's primary mirror had a tiny flaw, just 2 microns off, but enough to blur every image. The public mocked it. Congress debated killing it, but in 1993, astronauts flew up to Hubble and installed a set of corrective optics, the equivalent of giving glasses to the telescope. And from that moment on, Hubble began to show us the universe as we had never seen it. Galaxies in collision, stars being born, light from the early universe, stretching across time. It was Hubble that gave us the famous Pillars of Creation image, towering clouds of dust in the Eagle Nebula. It was Hubble that performed the Hubble Deep Field, pointing at an apparently empty patch of sky for 10 days and revealing thousands of hidden galaxies, each teeming with stars. And Hubble didn't just take pictures. It helped measure the expansion rate of the universe. It identified exoplanet atmospheres. It observed supernovas, black holes, and the aftermath of cosmic collisions. For more than 3 decades, it operated above us, serviced and upgraded by astronauts on the space shuttle. It became not just a tool, but a symbol of vision, of clarity, of cosmic ambition. Even today, with newer telescopes in service, Hubble continues to operate. It still sends back images, still contributes to research, still reminds us of what happens when a civilization decides to look beyond its world. In many ways, astronomy split into 2 eras, before Hubble and after. And even now, orbiting 540 kilometers above our heads, Hubble remains one of the greatest scientific instruments ever built. If Hubble opened our eyes, the James Webb Space Telescope opened a new sense entirely. Launched in December 2021, after years of delays and engineering challenges, Webb was designed not to replace Hubble, but to extend our vision farther, deeper, and into wavelengths of light no human eye can see. Unlike Hubble, which orbits Earth, Webb was sent far beyond the Moon, nearly 1.5 million kilometers away, to a stable point known as L2. There, shielded from the sun by a massive tennis court-sized sun shield, it can observe the coldest, faintest objects in the universe. Webb's specialty is infrared light, radiation, just beyond the red edge of the visible spectrum. Infrared lets us see what's hidden, the earliest galaxies, shrouded in cosmic dust, the birthplaces of stars and planets, the light from the dawn of time, stretched and cooled by billions of years of cosmic expansion. Its mirror, made of 18 gold-coated hexagonal segments, is over 6.5 meters across, more than twice the size of Hubble's. Its sensors are tuned to such sensitivity that Webb can detect the chemical fingerprints in the atmospheres of exoplanets, including water vapor, carbon dioxide, and methane. Just months after deployment, Webb delivered its first images. Not just beautiful, but revolutionary. A galaxy cluster acting as a gravitational lens, bending the light of even older galaxies behind it. Clouds of gas swirling in star-forming regions. The spectral signature of an exoplanet's atmosphere, hinting at a world with clouds and possibly even a water cycle. But it's not just the data, it's the perspective. James Webb is a time machine. It sees things not as they are, but as they were billions of years ago. It lets us look back to the era when the first galaxies assembled, to the moments when light itself was still new. Where Hubble gave us beauty and clarity, Webb adds depth, a sense that the universe is not only large, but ancient, layered, and full of mysteries just starting to come into focus. It's not the final telescope, but it may be the most important one we've ever built. In the summer of 1977, 2 spacecraft were launched with a mission unlike any before, to explore the outer planets of the solar system, and then, if all went well, to keep going. They were called Voyager 1 and Voyager 2, and they were designed for durability, not elegance. Small, rugged, and powered by radioactive plutonium, these twin spacecraft carried instruments, cameras, and a golden phonograph record, the famous Voyager Golden Record, encoded with music, greetings, and sounds of Earth. No one expected them to last this long. Voyager 1 flew past Jupiter in 1979, sending back images of the planet's swirling clouds and volcanic eruptions on Io, the first time active volcanism was ever seen beyond Earth. A year later, it passed Saturn, capturing the stunning structure of its rings and revealing moons that had never been seen in detail. Voyager 2, taking a slightly different route, added 2 more firsts. It became the only spacecraft to visit Uranus and Neptune, discovering strange magnetic fields, ice giant weather patterns, and rings around planets where we never expected them. But the most remarkable part of the Voyager missions began after the planetary flybys. Instead of shutting down, they kept going. Voyager 1 crossed the boundary of the heliosphere, the bubble of solar wind surrounding our system, and entered interstellar space in 2012. Voyager 2 followed in 2018. They are now the farthest human-made objects from Earth, over 20 billion kilometers away, and still communicating. Every now and then, they send back data, measurements of cosmic rays, interstellar particles, and the shape of the solar system's edge. Tiny packets of information traveling for over 20 hours across the vast dark. The Voyagers also gave us a new perspective on home. In 1990, Voyager 1 turned its camera back toward Earth at Carl Sagan's request and took the iconic image known as the pale blue dot, a tiny speck of light suspended in a sunbeam. It reminded us how small we are and how far we've come. Today, the Voyagers are slowly going silent, one instrument at a time. But even as their signals fade, their legacy endures. They were not just explorers of the solar system. They were messengers, sent not just to planets, but to time itself. When it launched in 1997, Cassini was just another spacecraft with a long journey ahead. But when it arrived at Saturn 7 years later, it transformed into something else entirely, a window into one of the most mysterious regions of the solar system. For over 13 years, Cassini orbited Saturn, becoming one of the most productive and awe-inspiring missions NASA and the European Space Agency ever launched. It wasn't just the rings, although Cassini captured them in breathtaking detail, revealing their structure, thickness, and strange behaviors like spokes and waves that ripple through icy particles. It wasn't even just Saturn itself, with its massive storms, hexagonal polar vortex, and rapid rotation. What made Cassini extraordinary was the unexpected. Cassini carried with it a lander, Huygens, which detached in 2005 and descended to the surface of Titan, Saturn's largest moon. For the first time in history, we landed something on a world beyond Mars. And what it showed was stunning. A frozen landscape with lakes, rivers, and rain made of methane, and an atmosphere dense with organic chemistry. Titan looked alien, but strangely familiar. Then came Enceladus, a small, icy moon, once thought to be inert. But Cassini's instruments detected plumes of water vapor erupting from its south pole, geysers shooting into space through cracks in the ice. Cassini flew through those plumes, and inside them it found organic molecules, salt, and signs of warm, liquid water beneath the surface, suggesting a hidden ocean, possibly habitable. Cassini showed us that even in the cold, far reaches of the solar system, there are places where life might exist. Not in the way we imagined, not green fields or forests, but in oceans beneath ice, warmed by tidal forces and chemical energy. Its final mission was poetic. In 2017, with fuel running low, Cassini was directed to dive into Saturn's atmosphere, a planned destruction to avoid contaminating any potentially life-bearing moons. As it descended, it kept sending data until the very last moment, becoming one with the planet it had studied for more than a decade. Cassini didn't just explore Saturn, it redefined what we thought the outer solar system could be. Not empty, not lifeless, but dynamic, evolving, and full of possibilities. For most of human history, we didn't know if other planets existed beyond our own solar system. It wasn't that we thought Earth was alone. We just had no proof, no evidence, no way to see them. That changed in 2009 when NASA launched the Kepler Space Telescope, a mission so precise and so patient that it quietly rewrote the boundaries of what we believed. Kepler didn't look for planets the way you might think. It didn't take photographs of alien worlds. Instead, it stared at a single patch of sky filled with about 150,000 stars and waited for tiny dips in brightness, the telltale signs of a planet passing in front of its star, a technique called the transit method. Over the course of its mission, Kepler detected over 2,600 confirmed exoplanets and thousands more possible candidates. Some were massive gas giants close to their stars. Some were rocky. Some orbited in their star's habitable zone, where temperatures might allow for liquid water. But it wasn't just the numbers. It was the realization that planets are common, that most stars likely have them, that Earth is not rare, but perhaps typical, and that the Milky Way may contain billions of Earth-like worlds. Kepler found planets that orbit two stars, like Tatooine, planets with year lengths of just a few days, and some so distant from their stars that their orbits stretch for decades. And the telescope faced challenges. In 2013, it lost 2 of its 4 reaction wheels, essential for pointing. But engineers reprogrammed the mission, creating K2, a second phase that allowed Kepler to continue observations using solar pressure for balance. Even after its retirement in 2018, Kepler's data is still yielding discoveries. Astronomers continue mining its archive for signals, and its legacy lives on in every exoplanet found today. Kepler didn't just find planets, it opened a door. A quiet, steady sentinel that showed us our night sky is filled with other worlds, some perhaps like our own, waiting to be understood. When Kepler's mission came to an end, it didn't leave behind a void. It passed the torch. And the telescope that caught it was TESS, the Transiting Exoplanet Survey satellite, launched in 2018 with a bold new ambition to search the entire sky. Unlike Kepler, which focused on one patch of stars, TESS was designed to be broad and fast. It divides the sky into sectors, observing each one for nearly a month, covering 85% of the sky over 2 years. Its goal? To find planets around the brightest, nearest stars, the ones we might study up close someday. Like Kepler, TESS uses the transit method, looking for dimming light as a planet crosses in front of its star. But because its targets are closer and brighter, astronomers can follow up with ground-based telescopes and powerful instruments like the James Webb Space Telescope, probing atmospheres and searching for biosignatures. TESS has already discovered thousands of candidate exoplanets, including super-Earths, mini-Neptunes, and even planets in multi-star systems. Some orbit stars just dozens of light years away, cosmic neighbors by galactic standards. One of TESS's strengths is speed. Its cameras capture wide fields with high cadence, allowing it to catch short-period planets, ones that orbit quickly and offer frequent transits. That means confirmation comes faster, data comes faster, and discoveries stack up faster. But TESS isn't just about exoplanets. Its constant monitoring of bright stars has made it valuable for stellar physics, variable stars, supernovae, and even the detection of asteroseismic activity, the gentle pulsations that reveal a star's internal structure. In some ways, TESS feels like a bridge. It connects the era of Kepler's deep stare to a future of precision spectroscopy, direct imaging, and atmospheric analysis. It scouts targets that larger telescopes will study in detail. TESS reminds us that the search for other worlds isn't slowing down. It's accelerating, spreading across the sky, star by star, light curve by light curve. The more we look, the more we find. And TESS ensures we don't miss what's right in front of us. Most space missions look outward, towards stars, planets, galaxies beyond. But some of the most vital telescopes look inward, toward the one star we can't live without. The Solar and Heliospheric Observatory, or SOHO, is one of them. Launched in 1995, SOHO was a joint project between NASA and the European Space Agency, designed not just for solar science, but for space weather forecasting, a concept that would grow more critical with every passing year. Orbiting around the Lagrange point L1, about 1.5 million kilometers from Earth, SOHO has a continuous, uninterrupted view of the Sun. It observes everything from the surface of the Sun to the solar wind, the stream of charged particles that flows outward across the solar system. SOHO's primary mission was to study the Sun's interior and atmosphere. It uses helioseismology, the study of sound waves traveling inside the Sun, to map its internal dynamics. It captures the structure of the corona, the outer atmosphere that mysteriously burns hotter than the surface, and it tracks coronal mass ejections, or CMEs, immense bursts of plasma and magnetic fields that can slam into Earth, disrupting satellites, power grids, and communications. Thanks to SOHO, we've learned how to predict solar storms. It acts as an early warning system, giving us precious minutes or hours to protect vulnerable infrastructure. But SOHO also became something unexpected, a comet hunter. Its instruments, designed to monitor the solar environment, have detected over 4,000 comets, many of them sun grazers, icy bodies that swing perilously close to the Sun and often disintegrate. SOHO wasn't meant to last this long, yet decades later, it's still operational, still watching, still feeding scientists with real-time solar data, which not only protects Earth, but deepens our understanding of the star that fuels our climate, drives our weather, and defines the rhythm of life on this planet. In a way, Soho reminds us that our sun is not a steady flame, but a dynamic, restless sphere of fusion, pulsing with cycles, storms, and sudden bursts of energy. And in watching it closely, we're not just doing science. We're learning how to live safely in the shadow of a star. Most of the universe is invisible to human eyes. We see only a narrow sliver of the electromagnetic spectrum, the same way an old piano plays just a few keys of an infinite keyboard. But some of the most violent, mysterious, and energetic phenomena in the cosmos play in the high, bright notes of X-rays. To hear them, we needed a new kind of telescope. We built Chandra, launched by NASA in 1999 aboard the Space Shuttle Columbia. The Chandra X-ray Observatory was unlike any telescope before it. It wasn't about stars and galaxies in the usual sense. It was about neutron stars, black holes, supernova remnants, and the glowing gas in galaxy clusters that no other telescope could fully reveal. Chandra had to be placed in a high elliptical orbit, far above Earth's atmosphere, because X-rays from space don't reach the ground. Its orbit takes it 1/3 of the way to the moon, allowing for long, uninterrupted observations. Its optics are equally unusual. Unlike visible light telescopes that use mirrors to reflect light directly, Chandra's X-ray mirrors are nested in concentric cylinders, angled to graze incoming X-rays, focusing them delicately without absorbing their energy. The results have been stunning. Chandra revealed the structure of supernova remnants, like the famous Cassiopeia A, exposing shock waves and high-energy particles. It observed the jets of matter launched from black holes, moving at near light speed. It showed that galaxy clusters are filled with hot, X-ray emitting gas, evidence of dark matter sculpting their shapes. It also deepened our understanding of our own galaxy, imaging the chaotic center of the Milky Way, where a supermassive black hole silently shapes the motion of stars. Perhaps most importantly, Chandra made the invisible visible. It showed that the universe is not quiet. It is active, energetic, explosive, and constantly in motion, even when seen through the cold, sterile light of high-energy radiation. Even after more than 2 decades in space, Chandra remains the most sensitive X-ray telescope ever built. It doesn't show us beauty in the classical sense, but it reveals the bones and fire of the cosmos, the engines that power the galaxy and leave behind the ashes of creation. If Chandra gave us X-rays and Hubble gave us visible light, then Spitzer let us see the universe in a glow we rarely think about, the infrared. It was a telescope built not to see what shines, but what radiates, what lingers with warmth, even in the coldest reaches of space. Launched in 2003, the Spitzer Space Telescope was the final member of NASA's Great Observatories program, joining Hubble, Chandra, and Compton. Its specialty was infrared astronomy, and that meant seeing what lies behind dust, beneath the surface, and beyond the reach of ordinary light. Infrared light is the domain of cool stars, stellar nurseries, planet-forming disks, and distant galaxies whose light has been stretched by cosmic expansion. And because Earth's atmosphere absorbs most infrared radiation, Spitzers had to operate in space and stay cold, very cold. To do its job, Spitzer was chilled with liquid helium, reaching temperatures just a few degrees above absolute zero. Only then could it detect the faint heat signatures coming from billions of light years away. Spitzer discovered exoplanet atmospheres long before JWST. It mapped dusty disks where planets were forming. It revealed the structure of our own Milky Way, hidden behind veils of interstellar dust, and it peered deep into galaxy clusters, identifying some of the most distant galaxies ever observed at the time. One of its most iconic discoveries came not from galaxies, but from a single compact system, TRAPPIST-1, a star with 7 Earth-sized planets, some of them potentially habitable. Spitzer's precise measurements helped characterize their orbits, sizes, and possible compositions, setting the stage for future study. Spitzer was decommissioned in 2020 after 16 years of operation, far longer than expected. Its infrared eyes faded, but its legacy remains. It taught us that heat lingers where we least expect it, that the young, the hidden, and the ancient all emit their quiet warmth, and that sometimes, to see the universe most clearly, you have to look where the light doesn't shine, but where it still softly glows. Imagine trying to map a forest while standing inside it, not just its shape, but the position and motion of every tree. That's what Gaia set out to do for our galaxy. Launched by the European Space Agency in 2013, Gaia is a quiet spacecraft with an enormous task: to create the most detailed 3D map of the Milky Way ever attempted. Not a photograph, not an impression, a census of stars, measured with exquisite precision. Gaia orbits around Lagrange point L2, a gravitationally stable spot about 1.5 million kilometers from Earth. There, it scans the sky methodically, tracking the position, distance, motion, and brightness of stars, again and again over years. Its instruments can detect minute shifts in a star's position, the width of a human hair seen from 1,000 kilometers away. From this, Gaia calculates not just where stars are, but how they move, how fast, and even how old they might be. The result? A revolution in stellar cartography. Gaia has mapped over 2 billion stars, along with hundreds of thousands of asteroids, exoplanets, quasars, and distant galaxies. It revealed that the Milky Way is not a calm, flat disk, but a writhing, dynamic structure, rippled by ancient collisions with smaller galaxies. It showed how stars stream through space in families, moving groups, clusters, and remnants of galactic mergers. We've also learned about the mass and shape of the Milky Way, the motion of its arms, and the location of mysterious features like the galactic warp, a bend in the disk that twists like a ripple on a pond. Gaia's data feeds into almost every branch of astronomy. It's used to calibrate distances to supernovas, to track rogue stars flung from the galactic center, to study the dark matter halo that invisibly cradles our galaxy. It's not a flashy mission. There are no close-up images or dramatic discoveries. But Gaia is a foundation, a quiet, steady observer, transforming our understanding of where we are and where we're going. In mapping the Milky Way, Gaia gives us a context, a place in the stars, a home not just in space, but in motion. High in the Chilean Andes, where the air is dry, thin, and still, there sits a forest of white radio dishes, not aimed at the Earth, but at the vast sky above. This is ALMA, the Atacama Large Millimeter/Submillimeter Array, and it doesn't see stars. It sees the places where stars are born. Unlike optical telescopes, which capture visible light, ALMA listens to some of the coldest and faintest signals in the universe, light at millimeter and submillimeter wavelengths. This light comes not from blazing suns or glowing galaxies, but from dust and gas, the raw ingredients of stars, planets, and even life itself. ALMA is made of 66 individual antennas spread across a desert plateau at 5,000 meters altitude. Each antenna can move, allowing the array to change its configuration like a zoom lens stretching across miles. Together, they act as one enormous telescope with remarkable resolution, able to peer into dense clouds that would block any ordinary view. What it sees is remarkable. ALMA has imaged protoplanetary disks around young stars, swirling structures where new planets are forming. It's revealed rings and gaps, signs of baby planets carving out paths in their dusty cradles. For the first time, we can observe not just the theory of planetary formation, but its actual process. ALMA also maps the chemistry of interstellar clouds, detecting complex organic molecules, precursors to amino acids and life in places where stars haven't even formed yet. It studies colliding galaxies, watching how gas compresses and ignites new waves of star birth. And it captures the faint whispers of galaxies at the edge of the observable universe, letting us look back billions of years. Its location, far from civilization, minimizes interference. Its precision, down to fractions of a millimeter in wavelength, opens a window into a universe we never knew we could see. ALMA doesn't show us the stars themselves. It shows us where they come from, the cold, dark nurseries that eventually light up the sky. And in doing so, it reminds us that even in silence and shadow, The universe is preparing its next act. For most of human history, the sun was untouchable, a blazing godlike presence in the sky, too bright to stare at, too hot to approach, too powerful to fully understand. But in 2018, NASA launched a mission that dared to cross a line no spacecraft had ever crossed before. Its name was the Parker Solar Probe, and its mission was simple yet bold: touch the sun. Named after solar physicist Eugene Parker, who first theorized the solar wind, the probe was built to dive into the sun's outer atmosphere, or corona, to understand what powers the solar wind and why the corona is millions of degrees hotter than the sun's surface. To survive the journey, Parker had to be engineered like no spacecraft before it. Its thermal shield is made of carbon composite foam, only 11 centimeters thick, but capable of withstanding temperatures over 1,400 degrees Celsius. Just behind that shield, the instruments stay at room temperature, in a pocket of calm amid the inferno. But it's not just heat that Parker endures. It flies at incredible speed, over 600,000 kilometers per hour, making it the fastest human-made object in history. And each orbit brings it closer to the sun, with repeated gravity assists from Venus gradually shrinking its path. As it dives into the corona, Parker measures magnetic fields, solar particles, plasma flows, and waves rippling through the solar atmosphere. It captures real-time solar wind data, helping scientists understand how the sun's energy escapes into space and how that energy can affect Earth. Already, Parker has rewritten what we thought we knew. It detected magnetic switchbacks, sudden reversals in the sun's magnetic field. It flew through the Alphen critical surface, the boundary where the solar wind becomes faster than the speed of wave propagation, effectively crossing into the sun's atmosphere. This isn't just about solar science. Understanding the sun's behavior helps us protect satellites, astronauts, and power grids from solar storms. It informs the future of space travel and space weather prediction. The Parker Solar Probe is still diving, still braving the light, still teaching us that even the most familiar object in the sky is full of secrets. It is, quite literally, a mission that brings us closer to our star than ever before. Jupiter is a planet of superlatives, the largest in the solar system, the fastest spinning, the one with the most moons, the strongest magnetic field, the wildest storms. For centuries, we saw its swirling clouds and giant red spot, but we didn't know what lay beneath. In 2016, that changed with the arrival of Juno, a NASA mission designed to unlock the secrets hiding beneath Jupiter's turbulent atmosphere. Unlike previous spacecraft that orbited far from the gas giant, Juno was built to fly closer than ever before, dipping into tight, elongated polar orbits that take it just a few thousand kilometers above Jupiter's cloud tops. From this vantage point, Juno collects data no other probe ever could. It maps gravitational variations to probe the deep interior. It measures magnetic fields to study Jupiter's powerful dynamo. It tracks microwave radiation to peer beneath the cloud layers, revealing a world of ammonia storms, jet streams, and chaotic circulation patterns. One of Juno's key questions: does Jupiter have a core? Early theories suggested a solid, rocky center, but Juno's data points to something stranger, a fuzzy, diluted core, possibly the result of a giant impact early in Jupiter's life. Juno also revealed that Jupiter's famous Great Red Spot is much deeper than expected, extending over 300 kilometers down, with swirling roots that penetrate the atmospheric layers. And then there's Jupiter's auroras, the largest in the solar system. Juno has shown that they're powered not just by solar particles, but by Jupiter's own rotation and magnetic environment, which whip plasma around the planet like an electric dynamo. Even the planet's moons have come into sharper focus. Juno has taken close-up images of Ganymede and Europa, preparing the way for future missions like Europa Clipper. With its solar panels stretched wide and its instruments hardened against radiation, Juno orbits a planet more massive than all the others combined. It doesn't just study Jupiter's weather, it explores its structure, origin, and evolution, giving us clues about how gas giants form in our solar system and beyond. And in unraveling Jupiter's mysteries, Juno reminds us of the scale and complexity of planets we once thought we knew, and how much more they still have to teach us. For most of its life, Pluto was a blurry smudge, distant, cold, and poorly understood. Even after decades of planetary exploration, it remained an enigma, orbiting in the frozen reaches of the Kuiper Belt. But in 2015, all of that changed. Enter New Horizons, a piano-sized NASA spacecraft that traveled more than 4.8 billion kilometers to give us our first ever close-up look at Pluto. Launched in 2006, New Horizons spent nearly a decade coasting through deep space, passing by Jupiter in a slingshot maneuver that shaved years off its journey. And when it finally arrived at Pluto in July 2015, the images it sent back stunned the world. We had expected a gray, lifeless rock. Instead, we found a world with a beating heart, quite literally. A vast, icy plain in the shape of a heart, named Tombaugh Regio, dominated the landscape. It was not static, it was active. Pluto has glaciers, mountains made of water ice, and possibly even cryovolcanoes. Its thin atmosphere expands and contracts as it moves along its elliptical orbit. It's a small world, yes, but one that challenges everything we thought we knew about geological activity on cold, distant bodies. But New Horizons didn't stop there. After Pluto, it ventured further into the Kuiper Belt, targeting a small ancient object called Arakoth. This contact binary, two icy lobes fused together, offered a glimpse into the early building blocks of the solar system. Arakoth is pristine, unchanged for over 4 billion years, and gave scientists a rare look at how planets may have formed from smaller bodies. New Horizons is still moving outward, carrying with it a small amount of Pluto's dust, a digital library of human culture, and the hopes of a species forever curious. Its instruments continue to study the environment at the edge of the sun's influence, the heliopause, the Kuiper Belt, and the transition into interstellar space. With each passing year, it adds new data to our understanding of the solar system's frontier. New Horizons wasn't just about Pluto. It was about the idea that no world is too far, too small, or too obscure to be worth exploring. Even on the coldest edge of sunlight, there are stories waiting to be told. For as long as we've known about black holes, they've lived in the realm of theory, invisible monsters, predicted by Einstein, suspected by observation, but never seen. By definition, nothing escapes them, not even light. So how do you take a picture of the unseeable? In 2019, the world witnessed a scientific milestone. The first ever image of a black hole's shadow, captured by a project called the Event Horizon Telescope, or EHT. But the EHT isn't a single telescope. It's a global network of radio observatories, synchronized to act as one Earth-sized eye. From the Atacama Desert to Hawaii, from Greenland to the South Pole, each telescope records its slice of the sky. The data is so massive it can't be sent digitally. It has to be physically shipped on hard drives and processed together with atomic clock precision. The target? Messier 87, a giant elliptical galaxy 55 million light-years away, home to a supermassive black hole with a mass of 6.5 billion suns. The result was iconic. A glowing ring of gas, heated to billions of degrees, orbiting a dark center, the event horizon, the point of no return. It wasn't a photo in the conventional sense. It was a reconstruction, the result of complex algorithms and years of collaboration between hundreds of scientists. But it confirmed what Einstein's theory had predicted, and it gave us our first real glimpse of the warping of space itself. Since then, the EHT has turned its gaze to other targets, including the black hole at the center of our own galaxy, Sagittarius A star. That image, released in 2022, showed a smaller, more chaotic ring, confirming once again that black holes are not science fiction. They are very real and very powerful. But the EHT is about more than just pictures. It allows scientists to test general relativity in extreme conditions. It provides insights into accretion disks, relativistic jets, and the behavior of matter at the edge of physics. It's helping us understand how galaxies evolve and how their hearts, often hidden, drive so much of what we see. The Event Horizon Telescope didn't just photograph a black hole, it made the invisible visible. It gave form to the abyss, and it reminded us that even the darkest corners of the universe are not beyond our reach. Most telescopes focus on stillness. They stare at one point in the skies for hours, days, even years, waiting for the faintest signals from the past to appear. But what if we built a telescope to do the opposite, to watch everything all at once, over and over again? That's the vision behind the Vera Rubin Observatory, a groundbreaking facility nearing completion in Chile. When operational, it will become the first telescope to survey the entire visible southern sky every few nights, not in snapshots, but in motion. At the heart of the observatory is the LSST camera, the largest digital camera ever built for astronomy. It weighs over 3 tons and boasts a resolution of 3.2 gigapixels. Each image it captures will cover an area of sky equivalent to 40 full moons, and it will do this every 30 seconds, night after night, for 10 years. This isn't just about making beautiful pictures. The Rubin Observatory is a time-domain telescope, a machine designed to capture the changing universe. It will detect supernovas the moment they explode, track asteroids that could pose a threat to Earth, and spot the subtle flickers that reveal exoplanets, black hole activity, or the gravitational tugs of dark matter. Over its 10-year mission, the observatory will build the most detailed 4D map of the universe ever created, tracking billions of objects not just in space, but through time. One of its most ambitious goals: to help unravel the mystery of dark energy, the force driving the accelerated expansion of the universe. By charting how galaxies move and cluster over billions of years, the Rubin Observatory may give us our clearest insight yet into the structure of space-time itself. It's named after Vera Rubin, the astronomer whose observations of galactic rotation first suggested the existence of dark matter. A fitting tribute for a telescope that, like Rubin, is determined to show us that the universe is not static, but alive with motion and mystery. When it begins full operation, the Vera Rubin Observatory will not be watching one thing. It will be watching everything. And in doing so, it may change not just what we see, but how we see it. For over a century, gravitational waves were a mathematical whisper, a strange prediction of Einstein's general relativity. He thought they were real, but doubted we'd ever detect them. After all, how could you measure ripples in the very fabric of space-time? And yet, in 2015, a faint signal traveled across the cosmos and gently nudged a pair of mirrors on Earth. The world changed in that moment because LIGO, the Laser Interferometer Gravitational Wave Observatory, had heard the universe ring. At its core, LIGO is a deceptively simple machine. Two long tunnels, each 4 kilometers in length, arranged in an L shape. Inside, laser beams bounce between mirrors, measuring the distance to within 1/10,000th the width of a proton. When a gravitational wave passes, it stretches space in one direction and compresses it in another, ever so slightly changing the length of the arms. It's a measurement so delicate that seismic noise, passing trucks, even thermal motion can interfere. That's why LIGO is so meticulously isolated, and why there are 2 detectors, one in Louisiana, one in Washington State, to confirm any true cosmic event. The first detection? 2 black holes merging 1.3 billion light years away. Their collision sent out gravitational ripples that reached us as a fleeting tremor in space-time. We didn't see it, we heard it. That chirp confirmed a century-old theory and opened an entirely new way of observing the universe through gravity itself. Since then, LIGO, joined by its European counterpart Virgo, has detected dozens more events. Black hole mergers, neutron star collisions, and even mixed systems that defy our expectations. One neutron star merger was also observed by traditional telescopes, a multi-messenger event that revealed not only gravitational waves, but light, gamma rays, and even heavy elements like gold and platinum being forged in the explosion. LIGO showed us that the universe is not silent. It vibrates, and those vibrations carry stories of cataclysm and creation, of massive objects warping space, of time itself being stirred. And we've only just begun to listen. With upgrades and next-generation observatories like LISA on the horizon, gravitational wave astronomy promises to reveal things no telescope ever could. Because some secrets don't shine. Some secrets echo. For years we waited, through delays, redesigns, and an anxious launch into the deep black of space. But when the James Webb Space Telescope, JWST, unfolded its golden mirrors and turned its gaze to the cosmos, the wait proved worth every second. Its first light images, released in July 2022, didn't just impress. They redefined what we thought possible in astronomy. The very first image, known as Webb's first deep field, showed a speck of sky no larger than a grain of sand held at arm's length. And yet, In that tiny sliver, there were thousands of galaxies, some stretching back over 13 billion years, distorted into graceful arcs by gravitational lensing. We weren't just looking far, we were looking deep into cosmic time. Another image captured the Carina Nebula, a vast stellar nursery where new stars are born. But unlike Hubble's ethereal blues and purples, Webb revealed towers of gas and dust glowing in infrared, showing stars forming within the clouds, places Hubble simply couldn't penetrate. Then came Stephan's Quintet, a group of interacting galaxies. Webb captured not only the dramatic collisions and streams of stars, but also the hidden details of dust and shock waves, the fingerprints of galactic evolution. And perhaps most striking, the image of the Southern Ring Nebula, the glowing shell of a dying star. Where past telescopes saw a fuzzy cloud, JWST resolved it into nested layers of gas, complex, structured, and heartbreakingly beautiful. But JWST didn't just send pictures. It also delivered spectroscopy, the ability to break light into its components and analyze the atmospheres of distant exoplanets. In one of its early triumphs, Webb detected water vapor in the atmosphere of K2-18b, a potentially habitable exoplanet, and found hints of carbon-bearing molecules, key to life as we know it. These first light images were more than pretty postcards. They were proof of concept, a demonstration of power. That JWST wasn't just a successor to Hubble, it was a leap forward into a new era. It sees the cold, the dusty, the distant, and the first. It sees what has never been seen. And with every image, it expands our view, not only of the universe, but of what we're capable of imagining. By the time Perseverance landed on Mars in 2021, NASA had already sent multiple rovers to the red planet. So what made this one different? The answer lies not just in the rover itself, but in the tiny helicopter it brought along. Perseverance is the most advanced robotic explorer ever sent to another world. Its mission? To seek signs of ancient life, collect samples for return to Earth, and test technologies for future human missions. But even with all its instruments, drills, and cameras, one of the boldest experiments was just 1.8 kilograms in size. That was Ingenuity, the first aircraft to fly on another planet. Flying on Mars is no easy feat. Its atmosphere is just 1% as dense as Earth's, making lift incredibly difficult. Yet in April 2021, Ingenuity rose into the thin Martian air, hovered, turned, and landed. With that, powered flight became interplanetary. Ingenuity was supposed to fly just 5 times. Instead, it flew dozens of missions, scouting terrain, testing flight in extreme conditions, and even helping guide Perseverance by mapping safe routes. It became not just a demonstration, but an essential partner. Meanwhile, Perseverance itself began a groundbreaking journey across Jezero Crater, an ancient lakebed believed to have once held water and possibly life. It drilled into Martian rock, cached samples in sealed tubes, and began the search for biosignatures, chemical clues that may hint at microbial life from billions of years ago. Perseverance also tested tools for the future. An experiment called MOXIE converted Martian CO2 into oxygen, a vital step for future astronauts. Its navigation systems used artificial intelligence to drive more safely and autonomously than any rover before it. Together, Perseverance and Ingenuity represent a new phase of exploration. Not just robotic scouting, but preparation for human presence. Not just static observation, but mobility and adaptability. They are the first steps in a plan to bring pieces of Mars back to Earth, and eventually, perhaps, to send humans there. And in every wheel track and whirring rotor, they remind us the boundary between possible and impossible is thinner than we think. Sometimes, all it takes is a little perseverance and a touch of ingenuity. Every great telescope we've launched has changed us. Hubble gave us the age of galaxies. Kepler gave us a universe of planets. Webb opened windows into the early cosmos. But what comes next? The future of astronomy lies in missions we've only begun to dream about. Projects like LUVOIR, HABEX, and other next-generation observatories that could redefine what it means to see the universe. Let's start with LUVOIR, the Large Ultraviolet Optical Infrared Surveyor. It's designed to be a kind of super Hubble, far larger and more powerful, with a mirror up to 15 meters across, nearly 5 times the diameter of JWST. LUVOIR would be capable of imaging Earth-like exoplanets around Sun-like stars, detecting biosignatures like oxygen, methane, and water vapor in their atmospheres. But LUVOIR isn't just about planets. It could map galaxies with unprecedented resolution, observe the formation of stars and black holes, and study cosmic structure on a grand scale. Its versatility would make it one of the most ambitious scientific instruments ever conceived. Then there's HABEX, the Habitable Exoplanet Observatory. More specialized than LUVOIR, its mission is focused: find other Earths. HABEX would use a starshade, a massive flower-shaped disk flying tens of thousands of kilometers ahead of the telescope, blocking starlight so faint planets can be seen beside their suns. Together, these missions aim to answer perhaps the biggest question in astronomy. Are we alone? But even beyond those, there are ideas taking shape. LISA, the Space-Based Gravitational Wave Observatory. Origins, designed to peer into the dusty birthplaces of stars and planets, and radio arrays on the moon's far side, shielded from Earth's interference. Each of these represents a shift, not just in capability, but in perspective. We're no longer content with glimpsing light from the past. We want to read the chemistry of alien skies. We want to hear the tremors of space-time. We want to search with intent. These future tools are not just instruments, they're acts of hope. They require decades of planning, international cooperation, and a willingness to invest in questions that may not have answers yet. But that's what astronomy is. A long, slow pursuit of clarity, of reaching farther, listening harder, and seeing what no one has seen before. The next great discovery may not come from a flash in the sky, but from the patient gaze of a machine we haven't built yet. And when we look back at this moment, we may realize this was the dawn of a new age of seeing.